Quantum mechanics has some real useful things when it comes to chemistry. Now, to do the actual quantum mechanics problems, you've got to have Math 254 kind of skills, calculus, all right? And it's all stuff you can do. But in this class, certainly the goal was never for you to know calculus before you took Chem 221. So we're going to look at the results of the equations from quantum mechanics and how those results can be used to place electrons around atoms and ions. And to talk about all this, we need to talk about what orbitals are and what shells and subshells are. And again, over on the right side, you can see some of the math models that are used, and there's some beautiful mathematics that can be pulled out of all this. But that's not where we want to go. We want to talk about the results of quantum mechanics, and there we can do that through a series of what are called quantum numbers. When you take quantum mechanics and you do the calculus, you end up seeing that orbitals, those little side things, actually are where the electrons hang out. All right. And orbitals, we're going to see, there's usually a lot of them. Orbitals are placed into subshells, and the subshells are further placed into shells. So orbitals are like, if you will, the room in a house. Subshells are kind of like the houses themselves. And you can think about shells as being like streets with houses on them. The shells have subshells, and the subshells have orbitals. The streets shells have houses subshells, and the houses subshells have orbitals or rooms inside them. And again, the orbitals are what going to hold the electrons and stuff inside. The shells are called, I have given a special name, they're called the principal quantum numbers, all right? And they literally are a number. So we're going to start using the symbol N for shell. And this is analogous to what Bohr did with the shell. N equals 1, 2, 3, 4, etc. Those are the same basic type of shell values we're going to use in this class. The principal quantum number will help us to determine the energy and size of the orbitals and subshells. So just like some streets are more popular than others, some shells will have more energy than other shells. It's really kind of interesting how this stuff all works out. Periodic table is actually based around these quantum numbers. Now we're going to see that with a little bit of exception here, the N equals 1 shell is going to have just hydrogen and helium, only those two elements. And the N equals 2 shell is going to be lithium through neon. And you can see N equals 3, N equals 4, and stuff like that. So the shell number is something you can actually see in the modern version of the periodic table. The period number on the periodic table is kind of where the shell is. And there's a few exceptions to it, and we'll talk about that. But it's kind of cool to see how the shell number is actually related to the period number on the periodic table. So there are these 4 quantum numbers, and if you know the quantum numbers for the electrons, you can figure out some really cool things about them. You can figure out the shape, what it kind of looks like, size, you can figure the energy and stuff like that. Very, very cool. So these quantum numbers, which are the direct result of the calculus from quantum mechanics, can tell a lot of information about the electrons. So let's look at what the 4 quantum numbers are. First of all, there's N, the shell number. And that's the one that comes from Bohr. And the shell, which is always a whole number, is really going to help us find the energy and the size and stuff like that. N is, like, again, kind of like a street with houses on it. All right, the N shell is going to be pretty important. L and M sub L are called the subshell and orbital, respectively. L is called the angular quantum number, and it relates to the subshell. So you're going to see that there are different kinds of houses, and the houses relate to the L. And just like houses look different, subshells will have different shapes, and we'll talk about that, but it's the L value that helps out. Now, m sub L, the magnetic quantum number, actually is what's going to be used to tell which orbital we're talking about, which orbital is within a subshell. And the magnetic quantum number can help you figure out the direction that the subshell is facing. And we'll talk about that a little bit. The fourth quantum number is called m sub s. It's called the spin quantum number. And it's going to help us figure out the spin of the electron. Electrons, we're going to see, spin either, if you will, like this way, or they spin the other way. And one way is given a positive 1/2, and the other one is given a negative 1/2. Spin is important, but we're going to focus more on spin in Chapter 6, Part 2, the next section. What we're going to do in this part, we're going to focus big time on N, L, and M sub L, and how they can be used to start putting electrons around atoms. The quantum numbers handout, which is in the companion or it's on the website, might be helpful. It's an overview of the NL, M sub L, and I believe M sub S quantum numbers. So it might help you while going through this if you get confused or if this stuff is brand new to you. Here's a little bit more breakdown on N, L, and M sub L. So N, the shell number, we already seen starts at whole numbers, starts at 1, and it goes in whole numbers up to, in theory, infinity. And the N value helps us to understand the size and the energy of the different systems. L, the angular quantum number, depends on N. L always starts at 0 and goes up to N minus 1. And we'll see examples of this here coming out. But anyway, the angular quantum number is really called the subshell, and it helps us to figure out the shape of the orbital, like what it looks like. And again, just like houses have different shapes, we're going to see that the subshells have different shapes as well. And then finally, to figure out the rooms in our house, or the number of pieces, if you will, in our subshell, we need the orbital. And M sub L, the magnetic quantum number, helps us out with that. So the magnetic quantum number, M sub L, depends on L. These are L's right here. And what that says is M sub L goes from minus L to positive L in whole numbers. So let's say that you had an L of 1. M sub L would be negative 1 to positive 1. M sub L would be negative 1, 0, and plus 1. The number of orbitals in a subshell equals 2L plus 1. So just a second ago, when L equals 1, I said there was M sub L of negative 1, 0, and plus 1, 3 values. Well, 2 times L plus 1, 2 times 1 plus 1, 3 orbitals. That's a quick way to get the number of orbitals when you know the L. But if nothing else right now, do realize that M sub L depends on L. If you don't know L, you can't really know M sub L. And L also depends on N. If you don't know N, it's hard to know what L is. You can make some kind of blanket things, but it's hard to know. And again, M sub S, which is the fourth one, we're going to look at in the next section. A common thing we'll look at in this section is how to tell which set is not a valid set of quantum numbers, all right? And here's the kind of things you want to look for. First of all, when you always start with N has to be a whole number larger than 0, and you can see for A, B, C, and D, those are all whole numbers, so that's not a problem. Now, L is the next one, and L has an N dependence, and L always starts at 0 and goes to N minus 1. All right, so for example, if N equals 4 on A, then L would go from 0 up to 3. So L would be 0, 1, 2, and 3, and L of 1 is one of those, so that's legit. If you go to the B there, L of 5 is okay, because if N is 6, L goes from 0 up to N minus 1. 6 minus 1 would be 5, so L of 5 is okay. But the third one, N equals 2, L goes from 0 up to N minus 1. If N equals 2, N minus 1 would be 2 minus 1, 1. L of 2 cannot exist when N equals 2. L can be no bigger than n minus 1. So the problem here is C. This is the quantum mechanic way to describe L. Sometimes it's just a regular L like it is down here with Emsabel, but the same idea. N and L cannot be the same. L can be no bigger than n minus 1, and that's important. Now, even though we didn't need to talk about it, let's talk about Emsabel as well. Emsabel has to be between negative L and positive L in whole numbers. So if L equals 1, Emsabel could be negative 1 like it is, 0 and plus 1. Those would be allowed values of Emsabel. On the next one, if L equals 5, Emsabel could be any number between negative 5 and positive 5, and 0 does count here as an example. On the next one, let's assume L of 2 was legit, so Emsabel would be somewhere between negative 2 and positive 2, so positive 1 is okay. And the last one, L equals 2, same thing, negative 2 to positive 2, negative 2 is legit. So those are the kind of things we'll be looking at when it comes down to these quantum numbers.